Gases expand like solid and liquid on heating, with the difference that the relative expansion of gases is much greater than that of solids of liquids. For the same rise of temperature on a hot summer day when the temperature is on the peak, the tube of a cycle bursts when placed in the direct sun. The air in the tube expands with the rise of temperature of the surrounding. Due to expansion, the air in the tube exerts pressure on the walls of the tube, which bursts. This is an example of expansion of gases due to rise of the temperature. However, gases expands not only with the rise of temperature and contract with fall of temperature. The change of pressure of a gas also brings about a change in its volume. Thus, if we want to see the effect pressure alone on the volume of a gas, we will have to keep its temperature constant. The effect of pressure on the volume of a gas defines a law called Boyle's law, first enunciated by Robert Boyle. Boyle's law, the law states that the volume of a given mass of a gas inversely proportional to its pressure provided the temperature is kept fixed. Since the volume of a gas varies with its pressure, Boyle's law so to see the effect of temperature on volume, we keep the pressure constant. The exact relation between the temperature and volume of a gas is given by a law called Charles' law, first enunciated by Jacques Charles. The law states that the volume of a given mass of a gas is directly proportional to its absolute temperature provided the pressure is constant if V and T stand respectively for volume and temperature of the gas. Since the volume varies directly with temperature, the graph plotted between these quantities is a straight line as shown in figure. If the straight line obtained is extended, it cuts the temperature axis minus 273 degree, which where the volume of the gas is, if existed, is zero. A gas with zero volume is an intangible concept. A gas with zero volume cannot exist because gas is a kind of matter which occupies space. As a matter of fact, the gas is liquefied much before reaching this point, and hence Charles' law cannot be applied as we discussed earlier. To minus 273 degree, which is equal to 0 K on absolute scale of temperature, is called absolute zero. Thus, according to Charles' law, absolute zero is the temperature at which the volume of a gas should be zero. Kinetic theory provides a better definition of absolute zero, according to which this is the temperature at which the all body molecules of material body. So far we have discussed the expansion of gases under restricted condition. One of the three state variables, temperature in Boyle's law and pressure in Charles' law, is kept fixed during expansion. We now change both the temperature and pressure simultaneously and see their combined effect on volume. An equation relating all the three quantities, pressure, volume and temperature is called general gas equation. We will use Boyle's law and Charles' law to obtain this equation. V and T be the pressure, volume and the temperature of gas according to Boyle's law. An insulated cylinder fitted with a piston contains oxygen at a temperature of 20 degrees centigrade and a pressure of 15 atm in a volume of 22 liters. The piston is lowered down, decreasing the volume of the gas to 16 liters and the temperature is raised to 25 degree centigrade. Assuming oxygen to behave like an ideal gas, what is the final pressure of the gas? The equal amounts of different substances, for example copper, iron and water, heat them for a given interval of time under the same flame so that they all absorb same amount of heat energy from the source. At the end of the interval, you will find that the rise in temperature is not the same for all. It is maximum for copper, minimum for water and intermediate for iron, although much greater than that of water. This shows that copper is heated quickly whereas water very slow. This means that if they are all heated so as to have the same rise in temperature, copper will need least amount of heat and the water the greatest one. For this purpose, the amount of heat needed depends on the nature of the substances in addition to its logical dependence on the mass and the rise in temperature of the substances. It is found experimentally that the amount of heat required is directly proportional to both the mass of the rises temperature of the substances. Thus, if is the amount of heat added to rise the temperature of mkg of a substance through where C is a constant and known as the specific heat capacity of the substance. It depends on the nature of the substances and is entirely independent of its mass and the rise in temperature. If C is so small for substances, the heat needed will also be small, and if it is large, the heat needed will also be large under the similar condition of mass and rise in temperature for all substances. The heat needed for this purpose will depend solely on their specific heats. The substance with large value of specific heat will need more heat as compared to that having low specific heat. We see that water has large heat capacity as compared to other substances. This means that water needs a lot of heat energy to warm up. A warm water has a good source of internal energy. Similarly, the loss of large amount of heat energy causes only a small drop in the temperature of water. This is the reason why the temperature of the sea rises and falls very slowly. The daily temperature variations in thus smaller near coastal areas. For the same reason, coastal areas and island keep cooler in summer and warmer in winter compared to island areas. Thus, due to high specific heat capacity of water, the coastal areas have moderate climate throughout the year. The high specific heat of water, as well as its cheapness and availability, amounts for its its use as the circulating liquid in central heating system and as a cooling liquid in car engine. Another common application is the use of hot water bottles to keep warm. This is due to ability of water to store a large amount of energy.